please subscribe to support the channel. In the vast cosmic ocean filled with billions of galaxies, each holding billions of stars, the question that has haunted humankind for centuries still echoes through the silence of space. Are we alone? Our tiny blue world, Earth, drifts through the Milky Way like a fragile jewel suspended in darkness. It's the only place we know where life exists, a small sanctuary protected by a delicate balance of atmosphere, water, and sunlight. But for as long as humans have looked up at the night sky, we've wondered if somewhere out there, beyond the reach of our solar system, another world like ours might be waiting. Now, imagine that beyond the familiar glimmer of our sun and the planets that orbit it, there lies another star, not so far away on the cosmic scale, harboring a planet that might, just might, be capable of sustaining life. A planet orbiting our nearest stellar neighbor, a planet we call Proxima Centauri b. This isn't just science fiction. This is one of the most fascinating and hopeful scientific discoveries of our time. Just over 4 light-years away, that's about 40 trillion kilometers, lies Proxima Centauri, the closest known star to our sun. Around it, astronomers have detected a planet, roughly the size of Earth, orbiting within the star's so-called habitable zone, the region where temperatures might be just right for liquid water to exist. That single discovery changed everything. It made the dream of finding another Earth not just possible, but tangible. For decades, scientists have scanned the cosmos, searching for distant exoplanets, worlds beyond our solar system, using ever more sophisticated telescopes and data analysis techniques. Thousands have been found, but most are too far away to visit, study, or even observe clearly. Yet Proxima Centauri b is different. It's close. It's near enough that with the right technology, we could one day send a probe, or perhaps even a human crew to explore it. The idea that another planet just a few light-years away could have oceans, weather, and maybe even alien life captures something deeply human. Our relentless curiosity and our longing for connection beyond Earth. In this journey, we're not just looking at a planet, we're gazing at a mirror held up to the universe, one that reflects both our scientific ingenuity and our existential yearning to know what lies beyond the stars. In today's deep exploration, we'll unravel everything about Proxima Centauri b, from what makes a planet habitable, to how it was discovered, to the challenges it faces from its volatile parent star. We'll explore what it might look like to stand on its surface, how future telescopes could uncover its secrets, and whether one day humanity could set foot there. Our nearest potentially habitable planet isn't some distant fantasy. It's a real place that may hold the key to understanding life's resilience across the cosmos. So sit back, open your mind to the stars, and let's embark on this incredible interstellar voyage, beginning right here, with the search for worlds beyond our own. The story of Proxima Centauri b and our quest to find another Earth begins with a simple but profound question. What does it truly mean for a planet to be habitable? In everyday conversation, the word habitable might suggest a place where humans could someday live, an Earth 2.0 with blue skies, flowing rivers, and lush forests. But in the language of astronomy and astrobiology, habitability carries a much more specific meaning, grounded in physics, chemistry, and the delicate balance between a planet and its parent star. When scientists describe a planet as potentially habitable, they are not necessarily saying that it's covered in life or even that it resembles Earth's vibrant ecosystems. Rather, they mean that the planet might have the right conditions for life as we know it to exist. the essential ingredients that allow biology to flourish: liquid water, a stable atmosphere, and energy from a nearby star. Water is the cornerstone of this definition. On Earth, everywhere we find liquid water, we find life, from the frozen Antarctic lakes to the boiling hydrothermal vents deep in the ocean. Water is a universal solvent. It enables complex molecules to interact, form, and evolve. Without it, the chemistry of life, at least the kind we understand, becomes almost impossible. So, the first criterion for habitability is simple. A planet must be capable of supporting liquid water on its surface. But that, of course, depends on many other factors, especially temperature. Too close to a star, and a planet becomes a scorched wasteland, like Venus, where oceans boil away under crushing heat. Too far, and it turns into a frozen desert, like Mars or the icy moons of Jupiter. That's where the concept of the habitable zone comes in. Often called the Goldilocks zone, it's the region around the star where the temperature is just right, not too hot, not too cold, for liquid water to exist. For our sun, this zone stretches roughly from just beyond the orbit of Venus to about where Mars resides. Earth sits beautifully within that range, allowing oceans and a mild climate to persist over billions of years. But habitability isn't only about distance. A planet could lie in the perfect orbit and still be lifeless if it lacks the second key ingredient, a stable and protective atmosphere. An atmosphere does far more than just give us something to breathe. It regulates temperature, protects against harmful radiation, and maintains surface pressure high enough for liquid water to exist. Without it, even a planet in the right spot could be barren. Take Mars, for example. It lies near the outer edge of our sun's habitable zone, yet it lost most of its atmosphere long ago. Today, it's a cold, desolate world where water can only exist as ice or vapor. A planet's atmosphere must also be chemically balanced. Too much carbon dioxide, and it becomes a greenhouse oven. Too little, and it freezes. The delicate interplay of gases like nitrogen, carbon dioxide, and oxygen determines how heat is trapped and distributed, shaping whether a world is stable or hostile. Energy is another critical factor. A planet needs a continuous source of energy, usually from its star, to drive weather, chemical reactions, and biological activity. But that energy must arrive in moderation. Red dwarf stars, like Proxima Centauri, emit less visible light than our sun, but they can unleash massive bursts of radiation in powerful flares. Such outbursts can strip away atmospheres or sterilize planetary surfaces, challenging the very idea of habitability. This means that being in the habitable zone doesn't automatically make a planet truly habitable. Scientists often speak of potential habitability, a cautious label acknowledging that many unknowns remain. A planet may lie in the right region and even have an Earth-like mass, but without an atmosphere, magnetic field, or geological activity, it could still be utterly lifeless. Then there's a matter of time. For life to develop and evolve, conditions must remain stable for long periods, millions, even billions of years. A planet that constantly faces catastrophic climate swings or intense radiation storms might never give life the chance to take hold. Earth's stability, maintained by its magnetic field, plate tectonics, and balanced carbon cycle, is one of the key reasons complex organisms were able to emerge here. Astrobiologists often refer to the circumstellar habitable zone, but newer models also consider a broader concept, the planetary habitable zone. This includes factors like internal heat, tidal forces, and chemical composition. For instance, moons like Europa or Enceladus lie far outside the sun's traditional habitable zone, yet they harbor subsurface oceans heated by tidal interactions, showing that habitability might come in many forms. In essence, a habitable planet is not necessarily an Earth clone. It could be larger or smaller, warmer or cooler, but as long as it meets a few universal criteria, liquid water, energy, atmosphere, and long-term stability, it enters the realm of possibility. This is why Proxima Centauri b has captivated scientists and dreamers alike. Despite being over 4 light-years away, it checks some of these boxes. It's rocky, roughly the same size as Earth, and it orbits within the habitable zone of its star. Yet, as we'll see later, it faces enormous challenges that test the very boundaries of habitability. Defining what makes a world habitable doesn't just tell us where to look, it reshapes how we see life itself. It forces us to ask, could life adapt to conditions far beyond Earth's norms? Could it thrive under a dim red sun or within perpetual twilight? These questions push the frontier of our imagination and our science. Every exoplanet discovered, every rocky sphere orbiting a distant star is a new experiment in nature's grand laboratory. Some may be too hot, others too cold, but a few, perhaps just a few, might rest in that delicate balance where chemistry becomes biology and lifeless matter begins to stir. And somewhere in that balance, orbiting the faint red light of our nearest stellar neighbor, lies a planet that may hold answers we've been searching for since the dawn of civilization. As we leave behind our understanding of what makes a planet habitable, it's time to meet the star that has given us our most tantalizing candidate. A small, faint ember in the darkness of space that might just illuminate the path to our next great discovery. The search for life beyond Earth is not merely a modern obsession born of technology. It's a continuation of one of humanity's oldest dreams. Every generation has sought meaning in the heavens, and each discovery we've made, from the first telescopes to the latest space probes, has reshaped our understanding of what might be possible. Centuries ago, when Galileo first lifted his telescope toward Jupiter and saw its moons, he shattered the illusion that Earth was the only world with companions. That moment marked a turning point. The cosmos was no longer a static dome painted with stars. It was a vast, dynamic expanse filled with countless worlds. In the centuries that followed, scientists began to imagine that many of those worlds might be planets orbiting distant suns, perhaps with their own oceans, mountains, and even living creatures. But imagination alone wasn't enough. To truly search for life, we needed to see beyond the limits of our own solar system. For much of human history, the stars seemed fixed, their light unchanging. It wasn't until the late 20th century that technology finally caught up with our curiosity. The first confirmed detection of an exoplanet, a planet orbiting another star, came in 1995, when scientists Michel Mayor and Didier Queloz discovered 51 Pegasi b. It was a gas giant, nothing like Earth, orbiting scorchingly close to its star. But its discovery opened the floodgates. Suddenly, what had once been a matter of speculation became a field of science. We realized that planets are not rare, they are everywhere. Since then, our tools for exploration have evolved with astonishing speed. Telescopes like Kepler, TESS, and the James Webb Telescope have transformed our view of the cosmos. Kepler, launched in 2009, stared unblinking at a patch of sky for years, watching for tiny dips in starlight, the telltale sign of a planet passing in front of its star. Each faint flicker in brightness represented a possible new world. By the time Kepler's mission ended, it had confirmed more than 2,600 exoplanets, many of them small and rocky like Earth. TESS, the Transiting Exoplanet Survey satellite, carried that legacy forward, scanning nearly the entire sky, refining our map of nearby planetary systems. Meanwhile, powerful ground-based observatories, using techniques like radio velocity measurement, have been able to detect the subtle gravitational wobbles of stars caused by orbiting planets. These wobbles, imperceptible to the human eye, have revealed worlds invisible to telescopes, hidden in the faint shimmer of starlight. And now, the James Webb Space Telescope, positioned 1 million miles from Earth, has taken this search to an entirely new level. With its unmatched infrared sensitivity, it can peer through cosmic dust, studying the atmospheres of distant planets, searching for the fingerprints of life, molecules like oxygen, methane, and water vapor. For the first time in history, we're not just finding planets, we're beginning to study their chemistry, their climates, even their potential to support biology. Our robotic explorers within the solar system have been just as important in shaping this quest. Missions to Mars, from Viking to Perseverance, have searched for signs of ancient life in the red planet's soil. Probes like Galileo, Cassini, and Juno have revealed that the moons of Jupiter and Saturn harbor vast oceans beneath their icy crusts, places where alien microbes could be hiding even now. These discoveries remind us that life might not need Earth-like conditions at all, that it could thrive in darkness, under ice, or near volcanic vents. But it's the discovery of exoplanets, especially those in the habitable zones of their stars, that has truly expanded our cosmic horizon. Every confirmed planet adds another data point to a vast and growing tapestry, each one challenging our assumptions about where and how life might arise. Some orbit blazing hot stars. Others circle cold red dwarfs. Some complete an orbit in mere days. Others take years. Yet among them, a few stand out. Planets that seem just right, balanced between extremes, where water could flow and chemistry could flourish. The search for life beyond Earth is also a search for ourselves, a reflection of our drive to understand our origins and our place in the universe. It's an endeavor that blends science, philosophy, and imagination. When astronomers look for life, they're not just looking for aliens. They're looking for evidence that life is a universal phenomenon, not a rare cosmic accident. Over time, our techniques have become so refined that we can now detect planets smaller than Earth, orbiting faint stars trillions of miles away. We can measure their mass, their composition, even their temperature. We can estimate whether they might have clouds or oceans. What once took centuries of speculation can now be determined with mathematics and light. And yet, despite all this progress, one thing remains elusive: proof. We have not yet found definitive evidence of life beyond our world, but what we have found are worlds that could host it, planets like Proxima Centauri b. In that sense, every discovery brings us one step closer. Each new exoplanet detected, each distant star studied, is part of an unfolding story, a story of humanity reaching into the unknown with instruments of glass, metal, and light. It is the continuation of an ancient dream, written now not in myth, but in data and discovery. From the first spark of curiosity that drove early astronomers to map the heavens, to the advanced observatories that now peer across interstellar space, our search for life is also a search for connection. We're trying to answer a question older than civilization itself. Is life a singular miracle, or a common thread woven through the fabric of the universe? And in that grand search, the closest glimmer of possibility lies not in some distant galaxy or inevitable nebula, but right next door, orbiting the faint red light of our nearest stellar neighbor. To understand our quest fully, we must now turn our attention to that quiet star that sits just beyond the edge of our solar family, holding secrets that might redefine our place in the cosmos. As our journey through the cosmos continues, our gaze turns to the nearest star beyond our sun, a small, faint ember that, despite its dim light, burns with immense scientific intrigue. It is here, just over 4 light-years away, that our attention settles on one of the most extraordinary and consequential discoveries in modern astronomy: Proxima Centauri, the star that has become synonymous with hope, mystery, and the possibility of life beyond our solar system. At first glance, Proxima Centauri might seem unremarkable. Through even the most powerful amateur telescopes, it appears as nothing more than a faint red dot lost among the backdrop of brighter stars that populate the southern skies. Yet, hidden within that tiny speck of light lies our nearest stellar neighbor, the closest star to the Sun, situated approximately 4.24 light-years, or roughly 40 trillion kilometers away from Earth. That distance may sound immense, but in cosmic terms, it places Proxima right in our galactic backyard. Proxima Centauri belongs to the Alpha Centauri star system, a trio of stars bound together by gravity. The two main stars, Alpha Centauri A and Alpha Centauri B, form a tight binary pair.
Both are more similar to our Sun, shining brightly in the night sky of the southern hemisphere. Orbiting far from them, however, like a distant cousin trailing behind the family, is Proxima Centauri. It's the smallest, faintest, and coolest member of the trio, yet paradoxically, the one that has captured the most attention in recent years. Proxima Centauri is classified as a red dwarf star, also known as an M-type star. These are by far the most common type of star in the Milky Way galaxy, making up nearly 75% of all stars. Red dwarfs are cosmic minimalists, small, dim, and remarkably long-lived. While our Sun blazes with intense luminosity and has a lifespan of about 10 billion years, Proxima Centauri, with only about 12% of the Sun's mass and 14% of its diameter, shines over 1,000 times more faintly, but will continue burning for trillions of years. Its fusion process is slow and steady, converting hydrogen to helium with such efficiency that it could outlive our Sun and still be glowing when most of the Milky Way's brighter stars have faded. But Proxima's faintness is also what makes it so difficult to observe. Even though it is our closest stellar neighbor, it cannot be seen with the naked eye. Its apparent magnitude, about 11, places it far below the threshold of human vision without optical aid. It's a reminder that cosmic proximity doesn't always equal visibility. Sometimes the most intriguing mysteries lie in the faintest glimmers. What makes Proxima particularly fascinating is the delicate balance of its environment. Its surface temperature hovers around 3,000 Kelvin, nearly half that of our Sun's, which gives it a deep reddish hue. It radiates most of its energy in the infrared spectrum rather than visible light, which profoundly affects the illumination and climate of any planet that might orbit it. A world around Proxima would not bask in bright sunlight, but rather exist beneath a perpetual twilight, its sky tinted with soft crimson and violet tones like an eternal sunset. However, red dwarfs like Proxima are known to be turbulent. Though they are stable in their fusion process, they can unleash sudden and violent bursts of energy known as stellar flares. These eruptions can increase the star's brightness by several magnitudes within minutes, releasing powerful waves of ultraviolet and X-ray radiation. Proxima Centauri is particularly active in this regard. Observations have shown that it flares frequently, making it one of the more volatile red dwarfs in our stellar neighborhood. This characteristic poses both a challenge and a puzzle for scientists studying its planets. Could life survive around such a temperamental star? Despite these outbursts, Proxima's faint light and small size make it an ideal candidate for planet detection. The subtle gravitational tug of an orbiting planet can cause measurable shifts in the star's motion, allowing astronomers to detect even small Earth-sized companions. And in 2016, this method led to one of the most groundbreaking discoveries in the history of astronomy: Proxima Centauri b, a planet roughly the size of Earth orbiting within the star's habitable zone.
The discovery electrified the scientific community. For the first time, a potentially habitable world had been found not in some distant, unreachable region of the galaxy, but orbiting the star next door. Proxima Centauri, once a mere footnote in astronomical catalogs, suddenly became a symbol of possibility, a gateway to a new era of interstellar exploration. To understand just how remarkable this is, we must consider the sheer scale of our galaxy. The Milky Way spans over 100,000 light-years, containing more than 200 billion stars. Among such staggering numbers, the fact that our nearest neighbor hosts a planet that might be habitable feels almost poetic, as if the universe is whispering that life may not be a rare phenomenon after all. Still, Proxima Centauri remains a star of paradoxes. Its diminutive size belies its powerful influence on the conversation about extraterrestrial life. It is both gentle and violent, ancient and enduring, quiet and yet fiercely unpredictable. Its faint light carries the promise of new worlds, but also the warning of harsh cosmic realities. The Alpha Centauri system as a whole adds further intrigue. Alpha Centauri A,
a yellow star much like our Sun, and Alpha Centauri b, a slightly smaller orange star, orbit one another in a graceful celestial waltz. Together, they form the bright double star seen from Earth's southern hemisphere, the third brightest object in our night sky. Proxima, though gravitationally bound to them, orbits much farther out, at a distance of over 13,000 astronomical units, nearly half a light year. It completes a slow orbit that takes hundreds of thousands of years, circling its brighter siblings like a solitary sentinel on the fringes of the system. When astronomers peer at Proxima through the eyes of powerful observatories, they are not just studying another red dwarf. They're looking at the most accessible star beyond our own solar system, the first stepping stone on humanity's journey into the wider galaxy. It represents both proximity and potential, a tangible target for future exploration, and perhaps, someday, a destination. The idea that the nearest star might host a world capable of supporting life reshapes how we see our place in the universe. For the first time, interstellar space doesn't feel infinitely vast. It feels within reach. The light of Proxima Centauri, faint though it may be, now shines in our collective imagination as the beacon of our next great adventure. And so, with this understanding of the star itself, its nature, its power, and its proximity, our journey naturally turns to the larger family it belongs to, the Alpha Centauri system, a triad of stars that together form the nearest stellar neighborhood to our Sun, and the stage upon which the story of Proxima b truly begins. To fully appreciate Proxima Centauri and its planet, we must step back and look at the broader cosmic stage it inhabits, the Alpha Centauri system, our closest stellar neighborhood beyond the Sun. This system is not just a single star. It is a complex, fascinating trio that has captured the attention of astronomers for generations. Understanding its structure, dynamics, and proximity to Earth allows us to grasp why the discovery of a potentially habitable world around Proxima is so extraordinary. Alpha Centauri is composed of 3 stars, bound together by gravity in a delicate cosmic dance. At the heart of this system are Alpha Centauri A and Alpha Centauri b, 2 bright stars orbiting one another in a tight binary pair. Alpha Centauri A is very similar to our Sun, a yellow G-type main sequence star with roughly 1.1 times the Sun's mass and slightly greater luminosity. Its partner, Alpha Centauri b, is a bit smaller and cooler, an orange K-type main sequence star with about 0.9 times the Sun's mass. Together, they form a gravitational duet, completing an orbit around each other every 79.91 Earth years. This binary pair dominates the system's light output and, from Earth, is visible in the southern hemisphere as a stunning double star, easily one of the brightest in the night sky. For centuries, they were studied primarily for their proximity and brightness, offering astronomers a laboratory to understand stellar behavior, dynamics, and the subtle gravitational interactions that govern binary systems. Yet the third member of the stellar family, Proxima Centauri, is far more elusive. Unlike the bright A and B stars, Proxima is a faint, small red dwarf that lurks at the outer edges of the system. Its separation from the central pair is enormous, over 13,000 astronomical units, or nearly half a light year, which makes it orbit the binary stars at a leisurely pace, taking hundreds of thousands of years to complete a single orbit. Though distant, it is gravitationally bound to Alpha Centauri A and B, forming a system that is both interconnected and dispersed across an immense spatial scale. This 3-star arrangement creates a unique neighborhood in our cosmic vicinity. Together, these stars constitute the nearest stellar system to the Sun, lying just 4.24 light-years from Earth. To put that in perspective, even though the Milky Way contains hundreds of billions of stars, this trio is our immediate neighbor, the closest possible laboratory for studying stars, planets, and potentially habitable worlds outside our own solar system. The proximity of Alpha Centauri is what makes it so compelling. While countless exoplanets have been discovered thousands or even tens of thousands of light years away, the Alpha Centauri system is reachable, at least theoretically, by future interstellar missions. Its closeness allows for unprecedented observation opportunities. Even small telescopes can detect faint variations in brightness, while advanced spectrographs can measure the gravitational wobble of its stars, revealing the presence of planets otherwise invisible to direct observation. Alpha Centauri A and B themselves are fascinating in terms of planetary potential. The binary nature of their orbit presents challenges for planet formation, as the gravitational pull of each star can destabilize certain orbits. However, recent simulations suggest that stable regions exist where Earth-sized planets could survive, particularly closer to either star individually. These zones, sometimes called circumstellar habitable zones, provide scientists with plausible targets for future planet searches. Proxima Centauri, being a distant third member of the system, enjoys a more isolated orbit. Its planets therefore are largely unaffected by the gravitational interference of A and B. This relative solitude makes it an ideal candidate for hosting planets that could maintain long-term stability, a critical requirement for life as we understand it. The discovery of Proxima b within this tranquil outer orbit is thus a natural consequence of both proximity and circumstance. It is far enough from the binary pair to avoid orbital disruption, yet close enough to allow us to study it in detail. The Alpha Centauri system also serves as a benchmark for understanding our stellar neighborhood. It's a microcosm of the galaxy, a diverse set of stars bound together, interacting over vast distances, each with the potential to host planets, moons, and possibly life. The fact that such a rich system lies just a few light years away emphasizes how interconnected and layered our cosmic neighborhood truly is. Beyond the scientific fascination, there is a poetic quality to the stellar triad. For centuries, humans have looked to the stars and wondered if we are alone. Now, within a distance that light can traverse in just over 4 years, we have 3 suns forming a miniature stellar neighborhood. One of these, the faint and fiery Proxima, quietly harbors a planet that might resemble our own, a tantalizing hint that life could exist just next door in the vast darkness. Exploring the Alpha Centauri system helps us contextualize Proxima Centauri b. While much of the excitement focuses on the planet and its potential habitability, the dynamics of the system itself, the interplay between bright binaries and a distant red dwarf, provide the essential backdrop. Understanding the system is akin to understanding the stage upon which a cosmic drama unfolds. Without knowing the stars, we cannot truly grasp the conditions, challenges, and possibilities for planets that orbit them. In essence, Alpha Centauri is our nearest laboratory for studying exoplanets, stellar interactions, and the potential for life beyond Earth. It represents both opportunity and mystery, the closest stars, the faintest secrets, and the possibility that the next great discovery, a second Earth, may be orbiting just beyond the reach of our current imagination. Within this 3-star system, our story turns to its most compelling member, the one that harbors a world capable of harboring life, Proxima Centauri b. With our understanding of Proxima Centauri and its place within the Alpha Centauri system, the stage is set for one of the most remarkable astronomical discoveries of the 21st century: the detection of Proxima Centauri b, a planet orbiting our nearest stellar neighbor. The story of its discovery is a testament to human ingenuity, patience, and the power of careful observation, as well as a reminder of how subtle the universe's clues can be when revealing its deepest secrets. Astronomers had long suspected that small, dim stars like Proxima Centauri might host planets. Red dwarfs are the most common type of star in the galaxy, and theories suggested that their long lifespans and relative stability could allow rocky planets to form and persist in orbit around them. However, the faintness of these stars made detecting planets a serious challenge. Traditional methods, such as observing a planet transit directly in front of its star, were less effective because Proxima's light is so dim. Astronomers needed a more sensitive approach, one that could detect the gravitational influence of a planet without relying on the direct light it reflects. The technique that made the discovery possible is known as the radial velocity method, or sometimes called the Doppler wobble method. This approach relies on the fundamental principle of gravity. A planet exerts a pull on its host star just as the star pulls on the planet. Although the star is far more massive and moves far less, this gravitational tug is detectable as a tiny back-and-forth motion along our line of sight. When the star moves toward Earth, its light is slightly blue-shifted. When it moves away, the light is red-shifted. By carefully measuring these shifts over time, astronomers can infer not only the presence of an orbiting planet, but also details about its mass and orbit. In the case of Proxima Centauri, a team of international astronomers led by Guillem Anglada Escude employed highly sensitive spectrographs to monitor the star's light with unprecedented precision. Over months of meticulous observation, they detected a consistent repeating pattern. Proxima Centauri was wobbling ever so slightly, completing a cycle roughly every 11.2 Earth days. The periodicity of this motion indicated the presence of a planet tugging gently but persistently on its host star. That discovery was confirmed in 2016, and the newfound world was designated Proxima Centauri b. It is a rocky planet, slightly larger than Earth, orbiting well within the star's habitable zone, the region where temperatures are suitable for liquid water to exist. The discovery instantly became a watershed moment in astronomy. Not only had we found a potentially habitable planet, but it was orbiting the closest star to our solar system. Suddenly, the dream of interstellar exploration felt just a little more tangible. The significance of the radio velocity detection cannot be overstated. Unlike methods that rely on a planet passing in front of its star, radio velocity allows astronomers to detect planets regardless of their orbital inclination, a crucial advantage for Proxima b, whose orbital alignment might never produce visible transits from Earth. Moreover, the method provides estimates of the planet's minimum mass, which in Proxima b's case was calculated at roughly 1.3 times the mass of Earth, making it the right size to be rocky rather than gaseous. It's remarkable to think that this entire discovery hinged on minuscule shifts in starlight, often amounting to just a few meters per second, roughly the walking speed of a human. To detect such subtle motion across the vast distance of over 4 light-years required the most sensitive instruments and the most patient minds in astronomy. Instruments such as the HARP spectrograph at La Silla Observatory in Chile were central to this effort, capable of detecting the tiniest variations in starlight caused by a distant planet. The discovery of Proxima b also opened new doors in exoplanet research. It proved that red dwarf stars, despite their smaller size and lower energy output, could host planets that are both rocky and potentially habitable. This finding shifted the focus of exoplanet searches dramatically, as red dwarfs constitute the majority of stars in the galaxy. In other words, the chances of finding Earth-sized planets in habitable zones increased dramatically once astronomers began to survey these abundant stellar neighbors.
Importantly, the announcement of Proxima Centauri b was not just a scientific milestone, it was a cultural and philosophical one. For the first time, humanity could point to a real, tangible world in our interstellar neighborhood and ask, with genuine hope, could life exist there? Could we one day reach it? Unlike distant exoplanets hundreds of light-years away, Proxima b is close enough that future generations might observe its surface directly, or even attempt interstellar exploration using advanced spacecraft. The radio velocity detection, combined with later observations, also revealed hints about the planet's orbit and environment. Proxima b orbits extremely close to its star, just 7.5 million kilometers away, roughly 5% of the Earth-Sun distance. Because Proxima Centauri is so faint, this proximity still allows the planet to receive a comparable amount of stellar energy to Earth. This precise alignment, combined with the planet's mass and composition, makes it a prime candidate for further study regarding habitability, atmospheres, and the potential presence of water. In the annals of astronomy, the discovery of Proxima Centauri b stands alongside other groundbreaking finds, but it holds a unique distinction. It is a neighbor.
This closeness not only enhances its scientific importance, but also fuels the imagination of engineers, explorers, and storytellers. It represents a tangible goal for humanity, a nearby world where some of the deepest questions about life, habitability, and our place in the universe could eventually be answered. The elegance of its discovery, observing a faint star's imperceptible wobble across the darkness of space, reflects the beauty of modern science. Subtlety, precision, and patience unveiling cosmic truths. Proxima Centauri b is not just a planet, it is a beacon of possibility. Proof that even in the vastness of interstellar space, remarkable discoveries are waiting for those who know how to look. Building on the remarkable discovery of Proxima Centauri b, it is essential to understand the physical and orbital characteristics that make this planet so captivating. Each fact about Proxima b not only defines its uniqueness, but also informs our speculation about its potential habitability. By examining its mass, orbit, distance from its star, and other planetary traits, we begin to picture the environment of a world that, despite being light years away, feels astonishingly close in our imagination. One of the first and most fundamental facts about Proxima b is its mass. Using the radial velocity method, astronomers were able to determine that this planet has a minimum mass of roughly 1.3 times that of Earth. This places Proxima b firmly in the category of a rocky planet, as opposed to a gas giant like Jupiter or Neptune. Its mass suggests that it could have a solid surface capable of supporting continents, oceans, and potentially life. A planet significantly more massive than Earth might have a crushing gravitational pull, while a much smaller one could struggle to retain an atmosphere. Proxima b's mass therefore sits in the sweet spot that makes it particularly intriguing for studies of habitability. The orbital period of Proxima b is another defining characteristic. It completes a full orbit around its parent star in just 11.2 Earth days. By comparison, Earth takes 365 days to orbit the Sun, and Mercury, the closest planet to our Sun, takes 88 days. Proxima b's extremely short year is a direct consequence of its proximity to Proxima Centauri, a red dwarf star that emits far less energy than the Sun. To receive a comparable amount of stellar energy, enough to maintain temperatures that could allow liquid water, the planet must orbit very close to its host star. This brings us to its distance from the star, roughly 7.5 million kilometers, or about 0.05 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, approximately 150 million kilometers, so Proxima b is extremely close to its dim star. Despite this tight orbit, the low luminosity of Proxima Centauri means the planet does not experience the extreme heat that would render it inhabitable. Its location places it squarely within the star's habitable zone, where conditions might allow water to exist as a liquid, a critical requirement for life as we know it. The planet's close orbit, however, introduces other dynamics. One major consequence is the likelihood of tidal locking. Because Proxima b orbits so near its star, gravitational interactions over millions of years would have slowed its rotation until one side constantly faces the star, while the other side remains in perpetual darkness. This would create a world of extremes, a day side bathed in constant red light and warmth, and the night side frozen in shadow. Understanding this tidal locking is essential to modeling the planet's climate, weather patterns, and potential habitability. Proxima b is also classified as a terrestrial exoplanet, meaning it is composed primarily of rock and metal rather than gases or ices. Its density, inferred from mass estimates and comparisons with Earth, suggests it could have a layered internal structure, including a solid crust, a mantle, and potentially a molten core. This internal structure would be crucial for generating a magnetic field, which in turn could protect the atmosphere from stellar radiation, a key factor in determining whether the planet could support life. Another notable aspect of Proxima b is its stellar energy intake, or insolation. Despite being close to Proxima Centauri, the planet receives only about 65% of the energy Earth receives from the Sun, due to the star's low luminosity. This might place the planet in a cooler range compared with Earth, but atmospheric conditions or greenhouse effects could potentially compensate, allowing liquid water to persist on the surface. Scientists use climate models to explore these possibilities, but the combination of proximity and stellar output creates a scenario unlike anything found in our solar system.
It's also important to consider that Proxima b likely experiences significant stellar radiation from its parent star. Red dwarfs like Proxima Centauri are prone to flares that emit powerful ultraviolet and X-ray radiation. A planet orbiting so close would be exposed to these bursts regularly, which could strip away its atmosphere or influence surface conditions. This makes understanding Proxima b's magnetic field and atmospheric retention even more critical for evaluating its potential habitability. From a geometric perspective, Proxima b's orbit is nearly circular, which is beneficial for climate stability. Eccentric orbits, those that are highly elongated, can cause extreme variations in temperature, making conditions less favorable for sustaining liquid water. A relatively circular orbit allows for more stable conditions over the course of its short 11-day year, though tidal locking still means that temperature extremes between the day and night sides remain a major factor. Though we currently have limited knowledge about its surface composition, Proxima b's mass and radius suggest that it could host a variety of environments: rocky plains, possible oceans, and even mountains or valleys. Unlike Earth, where plate tectonics help regulate climate and recycle carbon, it's unknown whether Proxima b possesses such activity, but its rocky nature makes it plausible. Volcanism, if present, could play a role in sustaining a habitable atmosphere or replenishing gases lost to stellar winds. Another intriguing factor is its orbital resonance with Proxima Centauri's rotation. Red dwarf stars like Proxima can have rotation periods that influence planetary climates through variable stellar activity. The interplay between the star's magnetic field, flare activity, and the planet's orbit introduces a dynamic system in which habitability is not solely determined by distance, but also by the complex interaction of celestial forces. In summary, the key planetary facts about Proxima Centauri b paint a compelling picture. A planet slightly more massive than Earth, orbiting extremely close to a faint red dwarf every 11 days, located within the habitable zone, and potentially rocky with the capacity for oceans or continents. These properties make it not only scientifically fascinating, but also a prime candidate for future observation, whether through telescopes or potential interstellar probes. Every fact, from mass to orbital period, contributes to the tantalizing possibility that this world could resemble our own, even if in exotic and unfamiliar ways. Proxima b's characteristics combine to form an exceptional opportunity for humanity. The first nearby exoplanet where habitability is plausible, where future missions might probe its atmosphere, and where for the first time the prospect of life outside Earth moves from abstract speculation to tangible investigation. As we examine Proxima Centauri b more closely, one of the most critical factors determining its potential to support life is its position relative to its parent star, its location in the habitable zone, often called the Goldilocks zone. This region is neither too hot nor too cold, but just right. The precise orbital distance where temperatures could allow liquid water to exist on a planet's surface. Understanding this concept is essential because water is the foundation of life as we know it. Proxima Centauri, as a red dwarf star, emits far less energy than our Sun, roughly 0.15% of the Sun's luminosity. While this might seem minuscule, it is sufficient to create a habitable zone extremely close to the star. For comparison, Earth orbits the Sun at 1 astronomical unit, 150 million kilometers, and receives just the right amount of energy to maintain its oceans and climate. For Proxima Centauri, however,
The habitable zone lies at a fraction of that distance, placing Proxima b only about 7.5 million kilometers from the star. Despite this tight orbit, the energy reaching the planet is similar in intensity to what Earth receives, placing it comfortably within the zone where water could remain liquid. The habitable zone is determined by multiple factors, not just the distance from the star. A planet must receive enough energy to keep water from freezing, but not so much that it boils away. Additionally, the planet's atmosphere plays a vital role in moderating temperature. Greenhouse gases, such as carbon dioxide or water vapor, can trap heat and extend the habitable zone farther from the star. Conversely, reflective clouds or thin atmosphere could reduce surface temperatures, moving the habitable zone inward. Proxima b's orbit appears to strike this delicate balance. Its orbital period of about 11.2 days means it completes its year extremely quickly compared to Earth. Yet its close proximity ensures that it intercepts enough energy to maintain a moderate climate, at least in theory. Climate models suggest that with a sufficient atmosphere, temperatures could allow liquid water to exist either on the surface or perhaps beneath the surface in oceans or subsurface reservoirs. This potential for water is what makes Proxima b a prime candidate for habitability. The concept of the habitable zone also accounts for the spectral type of the star. Red dwarfs emit most of the radiation in the infrared range, unlike our Sun, which peaks in visible light. This shift in energy output affects how heat is absorbed and retained by a planet's surface. For example, water and carbon dioxide absorb infrared radiation more efficiently, which could help maintain warmth on Proxima b, compensating for the lower total energy emitted by its star. However, being in the habitable zone does not guarantee that the planet is truly hospitable. There are numerous complicating factors, particularly for planets orbiting red dwarfs like Proxima Centauri. These stars are prone to intense stellar flares, sudden eruptions that release bursts of ultraviolet and X-ray radiation. Such activity can strip away atmospheres or irradiate the surface, potentially making life difficult or impossible. Despite this, the very fact that Proxima b remains in the habitable zone offers hope that it could retain an atmosphere, especially if a magnetic field or other protective mechanisms exist.
Another important consideration is the tidal locking of the planet. Proxima b likely always shows the same face to its star, meaning one hemisphere receives constant daylight, while the other is in perpetual darkness. This configuration could create extreme temperature differences between the two sides. However, climate models indicate that with an atmosphere capable of redistributing heat, or perhaps with oceans circulating energy, the planet could maintain temperate regions where liquid water persists. In other words, even tidally locked planets can remain habitable if conditions are favorable. The habitable zone is not static. Over time, stars gradually change in brightness and activity, which can shift the boundaries of this zone. Red dwarfs, like Proxima Centauri, are long-lived, remaining relatively stable for trillions of years, far longer than our Sun's expected lifetime of 10 billion years. This stability increases the chances that Proxima b could maintain habitable conditions for vast stretches of time, a crucial factor for the emergence and persistence of life. Scientists often emphasize the conservative and optimistic habitable zones. In the conservative model, only regions where temperatures are reliably suitable for liquid water are considered. The optimistic model expands the zone slightly, taking into account potential atmospheric or geological factors that could allow life even in marginal conditions. Proxima b's orbit lies comfortably within both definitions, making it one of the most promising nearby exoplanets for further study. Its position in the habitable zone also has profound implications for future observations. Since Proxima b is relatively close to Earth and receives just the right amount of energy to potentially host liquid water, telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope can study its atmosphere for signs of gases such as oxygen, methane, or water vapor. If such signatures are detected, it would provide the first concrete evidence of a planet that could support life outside our solar system.
The habitable zone concept highlights why Proxima Centauri b has captured the imagination of both scientists and the public. It is not merely an Earth-sized planet orbiting a nearby star. It is a world situated at the perfect distance to potentially support the chemistry of life. Its location, combined with its rocky nature and Earth-like mass, places it at the top of the list of nearby exoplanets worth investigating. Being in the habitable zone transforms Proxima b from a distant point of light into a planet of real interest, a world that could host oceans, climates, and even the complex chemical reactions that make life possible. It reminds us that the universe is not just vast and empty. It is structured in ways that allow life to emerge in the right conditions, and Proxima b sits at the threshold of those conditions. To understand Proxima Centauri b and its potential to support life, it's essential to explore the star it orbits. Red dwarfs, like Proxima Centauri, are a type of star that is both the most common and in many ways the most enigmatic in our galaxy. Despite its small size and faint glow, it has a profound influence on the planets that circle it, shaping their climate, atmosphere, and even their ability to host life. Red dwarfs like Proxima Centauri are classified as M-type main sequence stars. They are considerably smaller and cooler than stars like our Sun, which is a G-type star. Proxima has roughly 12% of the Sun's mass and about 14% of its diameter, making it minuscule in comparison. To put this into perspective, if the Sun were a basketball, Proxima would be closer in size to a tennis ball. Its diminutive size and mass result in a correspondingly low luminosity, which emits only 0.0015 times the energy of the Sun, which is why it appears so faint even though it is the closest star to our solar system. The star's surface temperature is approximately 3050 Kelvin, much cooler than the Sun's 5778 Kelvin. This lower temperature gives Proxima Centauri its characteristic red color, which dominates the light it emits. Unlike the Sun, whose light is bright and yellow-white, Proxima's radiation peaks in the infrared spectrum. This shift affects how planets absorb and redistribute heat. Proxima b, orbiting so close to the star, receives energy that is mostly in the infrared range, which may influence atmospheric dynamics, potential photosynthesis, and surface temperatures differently than on Earth. Proxima Centauri's dimness also defines the planet's orbital requirements. Because the star emits so little energy, any planet must orbit much closer than Earth does to the Sun in order to receive a comparable amount of warmth. This explains why Proxima b completes an orbit in just 11.2 Earth days at a distance of 7.5 million kilometers. While this is incredibly close compared to the Earth-Sun distance, the faintness of the star ensures that temperatures on the planet are not immediately extreme, allowing it to sit within the habitable zone. However, Proxima Centauri's characteristic as a red dwarf also introduced significant challenges for habitability. Red dwarfs are notorious for their stellar activity, including violent flares that release bursts of ultraviolet and X-ray radiation. These flares can increase the star's brightness dramatically for short periods, potentially stripping away a planet's atmosphere or irradiating its surface. Observations have revealed that Proxima Centauri is particularly active in this regard, regularly unleashing energetic flares that dwarf anything experienced on Earth.
Despite its volatility, Proxima Centauri has remarkable longevity. Its low mass allows it to burn hydrogen fuel very slowly, giving it a lifespan of trillions of years, far longer than the Sun's expected 10 billion-year lifetime. This extreme stability, in terms of its fusion process, provides a potential advantage for life. Planets orbiting Proxima could enjoy an incredibly long window in which conditions might remain conducive to biology. The slow evolution of red dwarfs means that, while flares are a hazard, the star's energy output is consistent over periods far exceeding the lifespans of most solar-type stars. Another important property is the star's magnetic field, which is intimately connected to its flaring behavior. Proxima Centauri's magnetic activity drives the release of charged particles during flares, creating stellar winds that could interact with a planet's magnetosphere. If Proxima b has a strong magnetic field of its own, it may deflect these particles, preserving its atmosphere and surface conditions. If not, these flares could gradually erode the atmosphere, challenging the planet's habitability. Proxima Centauri's small size also influences its gravitational environment. Being less massive than the Sun means its gravitational pull is weaker, which affects the orbital dynamics of nearby planets. The proximity of Proxima b ensures that the planet experiences strong tidal forces from the star, likely resulting in tidal locking, where one side of the planet perpetually faces the star while the other remains in darkness. This tidal locking has profound implications for climate, weather patterns, and potential habitability, as we will explore in later segments. Interestingly, the dimness and low luminosity of red dwarfs like Proxima Centauri have made them ideal targets for planet detection. Their small size and low brightness make it easier to detect subtle shifts in the star's motion caused by orbiting planets, as well as slight dips in brightness from planetary transits. This is one of the reasons why Proxima b, despite orbiting such a faint star, could be detected with current technology, and why it remains one of the most promising exoplanets for study. Finally, Proxima Centauri's characteristics also shape the potential appearance of its planets. The reddish light emitted by the star would bathe Proxima b in a perpetual soft crimson glow, vastly different from the bright white light of the Sun. Sunsets, if they exist on the planet, would appear muted, with a faint red or deep pink cast across the sky. Daylight would be dimmer, yet infrared radiation could still provide enough energy to warm the planet's surface, allowing for the possibility of liquid water. In summary, Proxima Centauri is a small, cool, dim, and long-lived red dwarf whose properties define every aspect of life and habitability on Proxima b. Its low luminosity necessitates close-in orbits, its frequent flares present both risks and challenges, and its slow evolution provides long-term stability. By understanding Proxima Centauri's characteristics, we gain insight into the environment in which its planet exists, an environment that is alien in many ways, yet tantalizingly familiar, with the potential to host a world that may resemble Earth in some critical respects. Even though Proxima Centauri b occupies the star's habitable zone, this promising location does not automatically guarantee that the planet could support life. The reality is far more complex. Being close to a red dwarf star like Proxima Centauri comes with a series of formidable challenges that could make life, at least life as we know it, extremely difficult to sustain. Understanding these challenges is crucial for evaluating the planet's habitability and for interpreting the significance of its discovery. One of the most significant hazards is stellar flares. Red dwarf stars, especially small active ones like Proxima Centauri, are prone to intense bursts of energy, sometimes dramatically increasing their brightness for minutes to hours. These flares emit powerful UV and X-ray radiation, which can have catastrophic effects on planets orbiting close by. For Proxima b, which orbits at only about 7.5 million kilometers from its star, roughly 0.05 astronomical units, such flares pose a direct threat to the atmosphere and surface conditions. Repeated exposure to high-energy radiation can gradually strip away a planet's atmosphere, a process known as atmospheric erosion. The charged particles and UV photons from flares can ionize gases in the upper atmosphere, causing them to escape into space. Over millions or billions of years, this could thin the atmosphere to the point where it can no longer sustain liquid water, regulate temperature, or protect any potential life from harmful radiation. For a planet so close to its host star, this is not a hypothetical risk. It is a real, ongoing process. Proxima Centauri's flares are not just infrequent bursts, they're frequent and unpredictable. Observations reveal that the star regularly experiences powerful outbursts, with some flares releasing more energy than the Sun emits in hours or even days. Unlike Earth, where the Sun's radiation is relatively steady and predictable, Proxima b would be exposed to sudden, extreme radiation events that could disrupt atmospheric chemistry, sterilize the surface, or even cause the loss of water molecules over time. Another challenge stems from the likely tidal locking of Proxima b. Because the planet orbits so close to its star, Gravitational interactions have probably slowed its rotation so that one hemisphere constantly faces Proxima Centauri while the other remains in perpetual darkness. This creates extreme temperature differences between the two sides. The day side could experience scorching heat and intense radiation, while the night side might plunge to frigid temperatures. Such conditions complicate the potential for stable climates and create regions where life might not be able to survive. Even if Proxima b retains an atmosphere, it must be exceptionally resilient to withstand these flares. A strong magnetic field could provide some protection by deflecting charged particles, much like Earth's magnetosphere shields us from the solar wind. However, it is currently unknown whether Proxima b has the magnetic field strong enough to survive billions of years of exposure. Without this shield, the atmosphere could gradually erode and the surface would be bombarded with radiation capable of breaking apart complex molecules necessary for life.
In addition to flares, red dwarfs like Proxima Centauri emit high levels of energetic particles through continuous stellar winds. Unlike the Sun, whose winds are relatively mild and predictable, Proxima's stellar wind is far stronger due to its lower mass and magnetic activity. This continuous bombardment could contribute to atmospheric loss, especially if the planet lacks protective mechanisms such as a thick atmosphere or a strong magnetic field. Over long periods, the combined effects of flares and stellar wind could render the planet inhospitable. The proximity to the star also affects the planet's potential for water retention. Being so close, Proxima b may have experienced intense heat during its early formation, possibly leading to the evaporation of water. If flares and stellar winds have been stripping away hydrogen and oxygen molecules over billions of years, the planet might now be a dry, rocky world rather than a watery haven. The possibility of oceans or liquid water depends heavily on whether enough water survived and whether atmospheric pressure is sufficient to prevent evaporation. Another, less obvious but critical challenge is radiation-induced chemistry in the atmosphere. UV and X-ray radiation can break down molecules like water vapor and methane, altering the atmospheric composition and potentially eliminating gases that would otherwise stabilize the climate or support life. This could create a cycle in which, even if water and an atmosphere exist, chemical reactions triggered by radiation continuously erode the planet's habitability. Finally, these challenges also impact the possibility of life emerging or persisting on Proxima b. Life on Earth developed over billions of years under relatively stable conditions. On a planet exposed to frequent high-energy flares, tidal locking, and potential atmospheric loss, the window for life to originate and evolve may be significantly narrower. Any life forms would need extraordinary adaptations to survive the intense radiation and extreme temperature variations. Yet, despite these formidable obstacles, Proxima b is still considered one of the most promising nearby exoplanets for habitability. Scientists speculate that protective mechanisms such as a strong magnetic field, a dense atmosphere, or subsurface water could mitigate the effects of flares. Oceans beneath ice, for instance, could shield life from radiation, much like the subsurface oceans thought to exist on Jupiter's moon Europa. Likewise, life could persist in temperate regions along the terminator, the narrow band between the perpetual day and night sides, where temperatures might be moderate enough to support liquid water. In essence, the challenges posed by Proxima Centauri's violent activity do not entirely rule out habitability, but they make it far more precarious than on Earth. Life, if it exists, would need to be resilient, adaptable, and possibly hidden beneath protective layers. Understanding these threats is critical for evaluating observational data, designing future missions, and modeling the planet's climate and potential biosignatures. While Proxima b's location in the habitable zone raises hope, the reality of its environment reminds us that habitability is never simple. The star that provides warmth and energy is the same star that unleashes potentially destructive flares. This duality, nurturing and threatening at once, highlights the delicate balance required for life to exist beyond our solar system. It is a reminder that in the universe, even proximity to a habitable zone does not guarantee that a planet is a haven for life. One of the most critical questions about Proxima Centauri b, and indeed one of the most significant for evaluating its habitability, is whether it has an atmosphere. The presence or absence of a stable atmosphere could mean the difference between a planet that is a barren, irradiated rock and one that has the potential to host liquid water and, by extension, life. Scientists have been analyzing every clue from Proxima b's mass and orbital characteristics to the behavior of its parent star in order to assess the likelihood that the planet retains an atmosphere despite the formidable challenges posed by its environment. Proxima b's proximity to its star is both a blessing and a curse. Its close orbit, at roughly 7.5 million kilometers, ensures that it receives sufficient energy to potentially support liquid water, placing it in the habitable zone. Yet this same proximity exposes it to intense stellar flares and a constant stream of energetic particles from Proxima Centauri's active magnetic field. Over billions of years, these forces could erode or even strip away an atmosphere entirely. Ultraviolet and X-ray radiation from flares can ionize molecules in the upper atmosphere, causing them to escape into space. This process, called atmospheric escape, is one of the greatest threats to Proxima b's ability to sustain life. Despite these dangers, there are several reasons to believe that Proxima b might retain an atmosphere. One possibility is that the planet developed a strong magnetic field, generated by a molten iron core and its interior. Similar to Earth's magnetosphere, a planetary magnetic field could deflect charged particles from stellar flares, shielding the atmosphere from erosion. While the planet's tidal locking could influence the dynamics of its magnetic field, many models suggest that a molten core is still sufficient to generate protective magnetic lines that extend far enough to preserve an atmosphere. The composition and density of the atmosphere, if it exists, would also play a crucial role in its survival. A thick atmosphere, rich in greenhouse gases like carbon dioxide, could absorb and distribute the star's energy more evenly across the planet, particularly between the perpetually illuminated day side and the frozen night side. This would not only help stabilize temperatures, but also provide a layer of protection from radiation. Conversely, a thin or sparse atmosphere would be far more vulnerable to erosion from Proxima Centauri's frequent flares.
Observations of other exoplanets and theoretical models provide additional insight. Studies of planets around red dwarfs suggest that, while close-in worlds are at risk from stellar activity, the presence of volatile elements like water and carbon dioxide, along with internal planetary processes such as volcanism, could replenish the atmosphere over time. Volcanic outgassing, for example, could release gases into the atmosphere that replace what is lost to erosion, creating a dynamic balance that allows the planet to maintain habitable conditions despite the star's harsh behavior. Proxima b's potential for an atmosphere also depends on its formation history. If the planet formed farther from its star and migrated inward, it may have retained a significant supply of volatiles like water and nitrogen, critical for building and sustaining an atmosphere. Alternatively, if it formed close to Proxima Centauri, it may have been exposed to extreme radiation early on, which could have depleted its volatile reserves and left the planet partially or fully stripped of atmospheric gases. Scientists are actively exploring both scenarios using sophisticated climate and planetary formation models. One intriguing possibility is that Proxima b may possess an atmosphere similar to Venus or Mars, thick, potentially toxic, or thin and tenuous, rather than Earth-like. Even a non-Earth-like atmosphere could provide valuable clues about the planet's geology, climate, and history. For instance, the detection of certain gases like carbon dioxide, oxygen, or methane could indicate ongoing geological processes, atmospheric replenishment, or even biological activity. Studying such an atmosphere would help scientists understand the limits of habitability around red dwarf stars, which differ significantly from Sun-like stars. Future telescopes will play a decisive role in resolving these uncertainties. Instruments such as the James Webb Space Telescope, or JWST, and the Extremely Large Telescope, or ELT, are capable of detecting atmospheric signatures by analyzing the light that passes through or is reflected off the planet's atmosphere. By observing spectral fingerprints, astronomers can identify specific molecules and assess the density, composition, and stability of the atmosphere. These observations will determine whether Proxima B's atmosphere is robust enough to support liquid water, or if the planet is instead an exposed, irradiated rock. There is also the possibility that Proxima B has a partial or patchy atmosphere, perhaps concentrated in regions of the planet less exposed to stellar radiation. Tidal locking could create a scenario where the day side loses atmospheric gases more rapidly, while the night side retains pockets of air, potentially forming stable climate belts near the terminator, the boundary between day and night. In such a scenario, life, if it exists, could be confined to narrow regions with moderate temperatures and sufficient protection from radiation. In short, the question of whether Proxima b has an atmosphere remains one of the most critical mysteries in exoplanet research. The balance between the destructive forces of stellar radiation and the protective mechanisms offered by magnetic fields, atmospheric thickness, and geological activity will ultimately determine the planet's habitability. While it may have lost some or most of its original atmosphere over billions of years, there is a plausible chance that it retains a layer thick enough to maintain surface water and moderate temperatures, at least in some regions. Understanding Proxima b's atmosphere is not only important for evaluating its potential for life, but also for guiding future observational strategies and interstellar exploration. A planet without an atmosphere is unlikely to host life as we know it, whereas even a thin, stable atmosphere could provide the conditions necessary for microbial life or even more complex ecosystems in protected regions. In this way, the atmosphere represents both the key to habitability and the greatest challenge posed by the proximity of a volatile red dwarf. Assuming Proxima Centauri b has managed to retain at least a portion of its atmosphere, the question naturally turns to one of the most tantalizing possibilities in astrobiology: the presence of water. Water is the essential ingredient for life as we know it, and its existence on Proxima b could transform our understanding of habitability beyond our solar system. Models and simulations have provided compelling scenarios suggesting that under the right conditions, Proxima b could harbor liquid water, whether on its surface, beneath an icy crust, or in deep subsurface reservoirs. The starting point for these models is the planet's position within the habitable zone. Proxima b orbits approximately 7.5 million kilometers from its parent star, a red dwarf emitting a fraction of the sun's energy. This proximity places the planet squarely within the range where temperatures might allow water to exist in liquid form. The exact conditions, however, depend on the presence and composition of the atmosphere. A dense atmosphere, rich in greenhouse gases like carbon dioxide, could trap heat and prevent water from freezing on the day side or sublimating from the night side, especially given the likely tidal locking of the planet. Climate models suggest several scenarios in which water could persist on Proxima b. On a tidally locked planet, heat redistribution plays a critical role. If the atmosphere is sufficiently thick, winds could transport warmth from the day side to the night side, preventing the permanent freezing of water in shadowed regions. This could create habitable regions along the terminator, the narrow band between the day and night sides, where temperatures remain moderate enough for liquid water to exist. Even if large areas of the day side are extremely hot or the night side extremely cold, oceans or lakes could survive in these transitional zones. Another possibility arises from the presence of subsurface water. Even if the planet's surface is exposed to harsh stellar radiation or experiences extreme temperature swings, water could be preserved beneath an icy crust or deep underground. Geological activity, such as volcanism or tidal heating caused by the gravitational pull of Proxima Centauri, could maintain liquid water beneath the surface, similar to the subsurface oceans believed to exist on moons like Europa or Enceladus in our solar system. These hidden reservoirs would be shielded from the star's violent flares and high-energy particles, offering a stable environment where life might persist despite surface hazards. The potential for water is further enhanced by the planet's mass and gravity. Proxima b, with roughly 1.3 times the mass of Earth, is likely capable of retaining volatiles such as water vapor and other gases over geological timescales. This mass is sufficient to maintain atmospheric pressure needed for water to remain liquid, assuming the atmosphere has not been entirely stripped by stellar activity. If an atmosphere exists, it would help regulate temperature and prevent water from escaping into space, providing a stable environment where oceans, lakes, or even rivers could form. Models also take into account the chemical interactions between the planet's surface, atmosphere, and any potential water. Carbon dioxide and water vapor could combine to create a greenhouse effect, trapping heat and keeping temperatures above freezing. Volcanic outgassing could replenish atmospheric gases and maintain a cycle of water vapor, clouds, and precipitation, potentially supporting a hydrological cycle reminiscent of Earth's. This dynamic interplay between geology and atmosphere is critical in determining whether water can persist over millions or billions of years. Interestingly, even partial or seasonal water coverage could create localized regions of habitability. Some models suggest that pools of liquid water could exist at the substellar point, the region of the planet that receives constant light, while ice might dominate the night side. Alternating cycles of melting and freezing could create dynamic water systems, potentially allowing microbial life to adapt to changing conditions. The concept of pocket oceans, or liquid reservoirs under ice, provides a pathway for life to survive on a planet that otherwise appears hostile at first glance. Observational data, although still limited, may soon provide clues about Proxima b's water content. Future telescopes like the James Webb Telescope or the Extremely Large Telescope aim to analyze the planet's atmosphere for water vapor and other key molecules. Detecting water signatures would confirm that the planet is not only theoretically habitable, but potentially active in terms of chemical processes essential for life. Spectroscopy could reveal whether water exists in gaseous, liquid, or frozen states, helping refine climate models and focusing research on regions most likely to host oceans or subsurface reservoirs. It's also worth noting that water could have been delivered to Proxima b during its formation. If the planet formed farther from its star, in a region rich in icy planetesimals, and migrated inward, it may have retained a substantial water inventory. Even if some water was lost during early stellar activity or bombardment, enough could remain to support oceans or subsurface bodies. This scenario is supported by studies of terrestrial planets in other systems, which suggests that close-in planets can still retain significant water if they formed with it or acquired it through late-stage impacts. The possibility of water on Proxima b is what makes it uniquely compelling among the thousands of exoplanets discovered so far. Its proximity, rocky composition, Earth-like mass, and location in the habitable zone combine to create a planet that is not just scientifically interesting, but potentially life-sustaining. Oceans or subsurface reservoirs, if they exist, could harbor the chemical ingredients and energy sources necessary for life to emerge, providing a tantalizing glimpse into what alien ecosystems might look like. Ultimately, water is the linchpin for the question of life on Proxima b. Its potential presence, whether as oceans shimmering in the star's faint red light, as ice-protected reservoirs below the surface, or as seasonal melt pools along the terminator, transforms a distant, rocky world into a candidate for life, a nearby laboratory for testing our understanding of planetary habitability. Even the mere possibility of water ignites the imagination, suggesting that within just over 4 light-years lies a planet where the familiar chemistry of life could be active, waiting for us to observe, explore, and perhaps one day visit. Proxima Centauri b's tidal locking is one of the most fascinating and defining features of this nearby exoplanet. Because it orbits so close to its star, just 7.5 million kilometers away, gravitational forces have likely slowed its rotation over millions of years until one side of the planet permanently faces Proxima Centauri, while the other side remains in perpetual darkness. This phenomenon, tidal locking, has profound implications for the planet's climate, temperature distribution, and overall habitability, creating a world with extremes unlike anything we experience on Earth.
On a tidally locked planet, the day side constantly receives the star's energy. For Proxima b, this means that the same hemisphere is bathed in a steady, dim red light emitted by its parent star. Unlike Earth, where sunlight moves across a surface and distributes warmth, the day side of Proxima b would receive uninterrupted stellar radiation.
Without sufficient atmospheric or oceanic circulation to redistribute heat, this side could become extremely hot, with temperatures potentially exceeding what life on Earth could tolerate. At the same time, because Proxima Centauri emits primarily infrared radiation, the intensity of heat would differ from that of sunlight on Earth, creating unique thermal conditions. Meanwhile, the night side of the planet lies in eternal darkness. Cut off from direct stellar energy, this hemisphere would tend to be extremely cold, possibly plunging far below the freezing point of water. In such an environment, any surface water could freeze completely, forming thick ice sheets. Without heat transport from the day side, the night side could be a frozen wasteland, potentially inhospitable to life. The key to habitability on a tidally locked planet lies in the distribution of heat between the day and night sides. If Proxima b possesses a sufficiently dense atmosphere, winds could transfer thermal energy from the day side to the night side, moderating temperature extremes. In some models, a thick atmosphere containing greenhouse gases like carbon dioxide and water vapor could circulate heat effectively enough to prevent the night side from freezing solid, while preventing the day side from overheating. Similarly, if the planet has liquid oceans, ocean currents could also play a critical role in distributing heat and maintaining regions of temperate climate. Another intriguing possibility is the existence of a terminator zone, the narrow region between the day and night sides. In this twilight band, temperatures might be moderate enough for liquid water to persist year-round. The terminator zone could represent a narrow but stable habitable region where life could potentially survive, shielded from the scorching heat of the day side and the frigid darkness of the night side. These habitable belts are a unique feature of tidally locked planets and are a central focus for climate models assessing Proxima b's habitability. Tidal locking also has implications for atmospheric and weather patterns. On the day side, constant heating could create strong convective currents, driving winds and storms that circulate air toward the night side. This circulation could generate extreme weather, including high-velocity winds or powerful storms along the terminator. Meanwhile, the night side, deprived of direct heat, could experience stable, frigid conditions or even pockets of permanent ice. The interaction between these zones could produce climates very different from anything on Earth, yet potentially capable of sustaining life if heat and energy are efficiently redistributed. Tidal locking also influences the diurnal perception of time. On Earth, day and night cycles help regulate biological rhythms and seasonal changes. On Proxima b, the day side experiences perpetual daylight, and the night side is in eternal darkness. Any life forms, if they exist, would need to adapt to these extreme, unchanging conditions. Photosynthetic organisms, for instance, might develop mechanisms to harness the constant dim red light, while organisms on the night side might rely entirely on geothermal or chemical energy sources.
Interestingly, tidal locking may even enhance habitability in certain respects. By stabilizing the planet's rotation, tidal locking reduces the likelihood of chaotic seasonal variations caused by axial tilt or irregular orbital dynamics. This stability, combined with an efficient heat redistribution system, could create long-term conditions suitable for the development of life. In other words, while tidal locking produces dramatic contrasts, it also provides a predictable and consistent environment, which is a key factor in sustaining stable ecosystems over geological timescales. Finally, the planet's tidal interactions with Proxima Centauri b generate internal heating, similar to the tidal forces affecting Jupiter's moon Io. This tidal heating could keep parts of the planet's interior warm, potentially maintaining subsurface oceans even if the surface is inhospitable. Such hidden reservoirs of liquid water would provide a stable refuge for life, protected from both the intense radiation of the day side and the frozen darkness of the night side. In summary, tidal locking creates a world of extremes on Proxima Centauri b. One hemisphere scorched by perpetual daylight, the other frozen in endless darkness. Yet this stark division also produces the potential for habitable regions along the terminator, and possibly subsurface environments shielded from the harsh surface conditions. The combination of atmospheric circulation, oceans, and tidal heating could transform this seemingly alien environment into a place where liquid water, and perhaps life, might exist. Understanding the day and night dynamics on Proxima b is therefore central to assessing its true potential as a habitable planet, revealing the delicate balance between stellar energy, planetary rotation, and atmospheric physics that shapes its climate. Visualizing what it might be like to stand on Proxima Centauri b is both awe-inspiring and humbling. Because the planet orbits a red dwarf star and is likely tidally locked, the experience of day and night would be unlike anything on Earth. The sky itself would appear alien yet strangely familiar, a reminder that while the laws of physics are universal, the conditions under which life might exist can vary dramatically across the cosmos. On the day side, the sky would be bathed in a constant red glow, produced by Proxima Centauri's dim, cool light. Unlike the bright white or blue sunlight we are accustomed to, the light here is soft, reddish, and diffuse, giving the landscape an almost surreal appearance. Shadows would be muted, and colors might appear shifted, as plants or rocks, if they exist, would reflect light differently under this red illumination. The constant presence of the star overhead would erase the concept of traditional day, replacing it with a steady, unchanging twilight that stretches across the sky for what, on Earth, would be the equivalent of an endless noon. Meanwhile, on the night side, the landscape plunges into deep frozen darkness. Devoid of stellar light, the night side could be illuminated only by distant starlight or perhaps faint glow from the day side if heat and light are redistributed through the atmosphere. The contrast between the two hemispheres would be stark, creating dramatic gradients of temperature and light. The perpetual dark would make this hemisphere inhospitable to surface life as we know it, yet hidden beneath ice or within subterranean oceans, life might find sanctuary from the harsh conditions above. Between these two extremes lies the terminator zone, a narrow twilight band encircling the planet where light and darkness meet. Here, temperatures could be moderate, making it one of the few potentially habitable regions. Standing in this zone, one might witness a perpetual sunset on the horizon, where the bright red light of Proxima Centauri gradually fades into the frozen night. Winds from the day side could blow across the terminator, carrying warmth and moisture, creating a dynamic environment where clouds form, swirl, and drift across the sky. The sky here could shift between deep crimson and dark indigo, casting long shadows over jagged rock formations, frozen plains, or possible pools of liquid water. The star itself, though dim, would appear much larger in the sky than our Sun due to Proxima b's proximity, about 38 times closer than Earth is to the Sun. This close distance would make Proxima Centauri appear as a vivid red disk, illuminating the surface with a soft, ambient light. Flares from the star could sporadically brighten the sky, erupting like brief bursts of red fireworks and bathing the landscape in intense radiation for minutes before fading back to normal. For any hypothetical life forms or explorers, these sudden flares would present both a challenge and a spectacular visual phenomenon. Looking outward, the view of the cosmos beyond the planet would be breathtaking. The night sky would be densely populated with distant stars, and perhaps the distant glow of the Alpha Centauri A and B stars, companions to Proxima Centauri b. Their light, though faint, would add a faint shimmer to the horizon, reminding an observer that Proxima b is part of a larger stellar neighborhood. The interplay of its own star's red light, the shadowed night side, and distant stars would create a panorama unlike any earthly landscape, simultaneously alien, beautiful, and awe-inspiring. If water exists on the planet, the reflections of Proxima Centauri on oceans or lakes along the terminator would produce surreal scenes. The red light glinting off liquid surfaces could create the appearance of crimson seas, their color shifting slightly depending on the angle of light and thickness of clouds. Ice formations on the night side might shimmer faintly under starlight, contrasting with the warm, glowing day side. The combination of frozen landscapes, liquid water, and atmospheric effects would make Proxima b's surface one of the most visually striking worlds imaginable.
Even the temperature perception would be unlike Earth. On the day side, constant exposure to infrared radiation could create a humid, heavy heat, while the night side would be frigid and dry.
Standing in the Terminator, one might feel a gentle gradient of temperature, a warm breeze from the day side brushing against the cold air drifting from the night side. The interplay of heat, light, and wind could create microclimates, localized regions where liquid water and potentially life could survive. The surface also invites speculation about how life, if it exists, might adapt to such conditions. On the day side, organisms could evolve pigments or reflective surfaces to cope with constant infrared light, while those on the night side could rely on geothermal heat or chemical energy sources. The Terminator zone could harbor life adapted to perpetual twilight, balancing between warmth and cold, light and shadow. This environment encourages us to rethink the possibilities of habitability beyond Earth, where life could exist under conditions that challenge everything we know about planetary ecosystems. From a human perspective, standing on Proxima b would be an experience that stretches the imagination. The red-tinted sky, perpetual twilight in the Terminator, frozen wastelands on the night side, and the fiery red disk of the star overhead would create a scene both alien and mesmerizing. The planet is a stark reminder of how diverse worlds in the universe can be, and how the combination of stellar properties, planetary orbit, and atmospheric dynamics can produce environments both extreme and potentially life-supporting. In essence, the view from the surface of Proxima Centauri b combines both beauty and peril. Breathtaking skies, alien light, and dramatic contrast between heat and cold, light and shadow. For scientists, this visualization is not mere imagination. It is a guide to understanding climate, habitability, and potential observational targets. For humanity, it is a glimpse into the vast possibilities of what worlds beyond our solar system might truly look like, and perhaps a spark for the dreams of exploration that may one day bring us there. The discovery of Proxima Centauri b has not only fueled our curiosity, but has also spurred a range of future missions and observational strategies aimed at understanding its atmosphere, climate, and potential for life. Because the planet lies just 4.24 light-years away, it is far closer than most other exoplanets, making it an ideal candidate for detailed study. Scientists are now leveraging cutting-edge technology and planning ambitious projects that could provide unprecedented insights into this nearby world. One of the most significant tools in this effort is the James Webb Space Telescope, JWST, which was launched to peer deeper into the cosmos than any previous telescope. JWST is equipped with highly sensitive infrared instruments, capable of detecting the faint signatures of planetary atmospheres. For Proxima b, JWST can measure how starlight is absorbed or scattered by the planet's atmosphere during transits, if they occur, or even analyze light reflected from the planet's surface. By detecting molecules such as water vapor, carbon dioxide, methane, or oxygen, JWST could provide the first concrete evidence that Proxima b maintains an atmosphere capable of supporting liquid water and perhaps life. Complementing JWST, the Extremely Large Telescope, ELT, being developed by the European Southern Observatory, ESO, promises to revolutionize our ability to study exoplanets. Scheduled to become operational in the near future, the ELT will feature a 39-meter primary mirror, allowing unprecedented resolution and sensitivity. With its adaptive optic systems, it could directly image planets like Proxima b and detect the spectral fingerprints of atmospheric gases. This would allow scientists to map temperature variations, detect cloud formations, and assess the planet's potential habitability. The combination of JWST and ELT could, for the first time, provide a multifaceted view of an Earth-sized exoplanet in our cosmic neighborhood. Beyond telescopes, other observational strategies are also being explored. Instruments such as the High-Accuracy Radio Velocity Planet Searcher, HARPS, and its successors continue to monitor Proxima Centauri for subtle variations in its motion caused by orbiting planets. These measurements refine our knowledge of Proxima b's orbit,
mass, and potential gravitational interactions with other planets in the system. Improved radio velocity measurements could even reveal additional planets, including smaller or more distant worlds that might complement Proxima b in the search for habitability. Space-based observatories like the Transiting Exoplanet Survey Satellite, TESS, and future missions, such as Plato, are contributing to our understanding of red dwarf systems more broadly. By monitoring thousands of stars, these missions increase the chances of detecting transits, which occur when a planet passes in front of its star and briefly dims its light. If Proxima b were to transit, even partially, astronomers could use this opportunity to study its atmosphere in unprecedented detail, analyzing how starlight filters through gases and identifying the chemical compounds present. The study of Proxima b's atmosphere is particularly important because it may reveal biosignatures, indicators of life. Certain gases, such as oxygen combined with methane, are difficult to produce through purely geological processes and could point to biological activity. Similarly, the presence of liquid water or complex cloud patterns could hint at active climate cycles that support life. Detecting such features on a planet so close to Earth would be revolutionary, marking the first time we have evidence of a potentially habitable exoplanet in our own stellar neighborhood. In addition to telescopes, there are ambitious interstellar observation concepts that aim to probe Proxima b more directly. Projects like Breakthrough Starshot envision sending tiny laser-propelled spacecraft to the Alpha Centauri system, including Proxima Centauri, at a fraction of the speed of light. While the spacecraft would not carry humans, they could transmit high-resolution images and spectroscopic data from the planet, providing detailed observations of its atmosphere, surface, and climate. These probes could help confirm whether water exists, whether clouds form, and whether the planet has surface features compatible with life. Ground-based observations also continue to improve. New instruments are being developed that can isolate planetary light from the overwhelming glare of red dwarfs. Techniques such as high-contrast imaging and coronagraphy allow astronomers to block out the star's light and detect the faint glow of reflected light from the planet. By combining these observations with spectral analysis, scientists hope to determine surface composition, cloud coverage, and even signs of surface water, adding a new layer of understanding to models of Proxima b's environment. Additionally, long-term monitoring of stellar activity is crucial. Because Proxima Centauri is highly active, understanding its flare frequency, intensity, and magnetic cycles will help scientists assess how much atmosphere the planet could retain and whether any life on the surface could survive. Observatories in space and on Earth are tracking the star continuously, providing critical data to inform climate models and habitability simulations for Proxima b. The combination of these missions and technologies represents the first time humanity has the tools to study a potentially habitable Earth-sized planet in such close proximity. In the coming decades, we may be able to determine whether Proxima b has water, an atmosphere, or even chemical signatures of life. Each observation, whether from JWST, ELT, or a future probe, brings us closer to answering one of humanity's oldest questions: are we alone in the universe?
In short, the future of observing Proxima Centauri b is both exciting and transformative. By combining advanced space telescopes, ground-based observatories, and ambitious interstellar probes, scientists are poised to investigate this nearby world in extraordinary detail. The results will not only illuminate the mysteries of Proxima b itself, but also inform our understanding of how common habitable worlds might be around red dwarf stars, potentially shaping the next era of exploration and discovery in our galaxy. The idea of interstellar travel has long captured human imagination, often relegated to science fiction. Yet with the discovery of Proxima Centauri b just 4.24 light-years away, this dream has begun to move closer to the realm of scientific plausibility. While conventional spacecraft would take tens of thousands of years to reach even the nearest star, innovative concepts like Breakthrough Starshot propose methods that could allow humanity to send probes to our nearest stellar neighbor within decades, opening up the possibility of direct exploration of Proxima b. Breakthrough Starshot, announced in 2016, is an ambitious project that aims to send tiny, wafer-sized spacecraft called starships to the Alpha Centauri system. Each probe is designed to weigh just a few grams, containing cameras, sensors, and communication devices. The plan involves using powerful Earth-based lasers to propel these chips to extraordinary speeds, up to 20% the speed of light. At such velocities, a probe could theoretically reach Proxima Centauri in just over 20 years, a timescale far shorter than the multi-millennial journeys that traditional propulsion methods would require. The laser propulsion concept is essential to making interstellar travel feasible. By focusing immense energy on a light sail attached to each starship, the laser imparts momentum, gradually accelerating the spacecraft to a significant fraction of the speed of light. While this involves enormous technical challenges, including maintaining laser alignment over millions of kilometers, protecting the chip from interstellar dust, and ensuring reliable communications across light years, it represents one of the few methods capable of sending physical objects beyond our solar system within a human lifetime. Once the probes reach Proxima Centauri, they could transmit high-resolution images and data back to Earth. Even though the signals would take 4.24 years to travel the distance, this would provide humanity with the first direct observations of a planet beyond our solar system. Instruments on the starships could analyze Proxima B's atmosphere, surface features, and possible signs of water, offering insights that telescopes alone cannot provide. This type of reconnaissance could answer key questions about habitability and provide critical data for future missions or even, far in the future, human exploration. The possibility of interstellar travel also raises questions about planetary protection and ethics. Sending probes at such high speeds introduces risks of collision with dust or other objects in space, which could damage or destroy the spacecraft. There is also the consideration of unintended impacts on the planetary environment. While the probes are minuscule and unlikely to pose a direct threat, these missions represent humanity's first steps in interacting with worlds beyond our solar system, necessitating careful planning and responsibility. Beyond Breakthrough Starshot, there are other theoretical propulsion concepts being explored. Nuclear pulse propulsion, for instance, envisions detonating controlled nuclear explosions behind the spacecraft to provide thrust, while fusion propulsion could harness the energy of controlled nuclear fusion reactions to accelerate massive spacecraft to a fraction of the speed of light. While these methods are still far from practical implementation, they illustrate the diversity of approaches being considered to achieve interstellar travel. Each method faces formidable challenges, including energy requirements, engineering complexity, and the need for materials that can withstand extreme conditions. Interstellar travel to Proxima Centauri also emphasizes the immensity of cosmic distances, even to our nearest neighbor. While 4.24 light-years seems close on a galactic scale, it is still roughly 40 trillion kilometers, far beyond the reach of conventional spacecraft. The development of laser-propelled probes and advanced propulsion technologies forces us to rethink both scale and time in space exploration, highlighting the gap between our ambitions and current technological capabilities.
Yet the proximity of Proxima b makes it uniquely accessible in the context of interstellar travel. Most exoplanets discovered lie tens or hundreds of light years away, making physical exploration virtually impossible with foreseeable technology. Proxima Centauri b, by contrast, is tantalizingly near. Even unmanned probes traveling at a fraction of light speed could reach it within decades, providing humanity with its first opportunity to directly study another world outside our solar system. The scientific payoff of such a mission would be immense, transforming exoplanet science, planetary habitability studies, and our understanding of nearby stars. The vision of sending spacecraft to Proxima b also inspires broader exploration goals. Beyond imaging and atmospheric analysis, these missions could test autonomous navigation and data collection techniques over interstellar distances, laying the groundwork for more ambitious missions in the future. They challenge engineers and scientists to push the boundaries of material science, energy generation, and communication, all while engaging the public in a shared vision of exploring worlds beyond our own. Ultimately, the idea of interstellar travel to Proxima Centauri b is a bridge between imagination and emerging science. While human travel to the planet remains far beyond our current technology, Tiny laser-propelled probes represent the first tangible step in reaching another star system. These missions would allow us to study the planet's atmosphere, climate, and potential habitability directly, providing data that telescopes can only approximate. The dream of touching another world, even with a robotic emissary, is closer than ever before, redefining humanity's place in the galaxy and expanding our understanding of the universe. Understanding the immense distance to Proxima Centauri b is crucial for appreciating the challenges of exploration and communication. While 4.24 light-years may sound small in the context of the galaxy, the Milky Way is over 100,000 light-years across. In practical terms, it represents an almost unfathomable expanse of space. A light-year, by definition, is the distance light travels in a single year, roughly 9.46 trillion kilometers, or 5.88 trillion miles. Multiplying this by 4.24 gives a staggering distance of approximately 40 trillion kilometers, or 25 trillion miles between Earth and Proxima b. To put this into perspective, the farthest humans have ever traveled is to the Moon, about 384,000 kilometers away. The distance to b is over 100 million times farther than that. Even spacecraft leaving our solar system, like Voyager 1, which has been traveling for over 45 years at a speed of roughly 17 kilometers per second, would take more than 70,000 years to reach Proxima Centauri. Conventional propulsion methods simply cannot bridge this gap within human lifetimes. Because Proxima Centauri is 4.24 light-years away, communication signals which travel at the speed of light take over 4 years to reach the planet. This delay applies in both directions. A message sent from Earth would take 4.24 years to arrive at Proxima b, and any reply would take the same amount of time to return. Therefore, a simple exchange of information would take over 8 years, making real-time communication impossible. For comparison, sending a message to the Moon takes only about 1.3 seconds, and even a Mars mission requires only 3 to 22 minutes, depending on orbital positions. The difference highlights the sheer scale of interstellar distances. This distance creates significant challenges for exploration. Robotic missions such as the proposed Breakthrough Starshot starships would need to be entirely autonomous, since we cannot guide them in real time. Every decision about navigation, data collection, and instrumentation must be pre-programmed, and the spacecraft must be able to adapt to unforeseen circumstances without human intervention. Any errors could be catastrophic, because correcting them remotely would take years. Even with autonomous probes, data transmission is limited. The further the probe, the weaker the signal reaching Earth. Tiny spacecraft traveling to Proxima Centauri would need highly sensitive receivers or extremely powerful transmitters to ensure that even a small amount of scientific data, images, atmospheric readings, or temperature measurements could be sent back. Advanced techniques in laser communication and data compression are being developed to address these issues, but the limits of physics still impose stringent constraints.
The vast distance also impacts planning for potential human exploration, which remains purely theoretical at present. A crewed mission to Proxima Centauri using conventional rockets would take tens of thousands of years. Even if we could travel at 10% of the speed of light, a feat far beyond current technology, the journey would still take over 40 years, requiring life support, shielding, and energy sources capable of sustaining humans for decades in deep space. For interstellar colonization, supply chains, communications, and psychological factors would present unprecedented challenges. Interstellar distances also affect our understanding of time and observation. Because light takes years to reach us, observing Proxima Centauri b is effectively seeing it as it was over 4 years ago. Any changes on the planet, whether atmospheric fluctuations, surface events, or signs of life, are delayed in reaching Earth. Similarly, if we detect a signal or feature of the planet today, it reflects conditions from 4 years in the past. This introduces an inherent lag in scientific understanding and underscores the isolation of interstellar exploration. Despite these obstacles, the proximity of Proxima Centauri is still remarkable.
Compared to the thousands of other known exoplanets, most of which lie tens, hundreds, or even thousands of light years away, Proxima b is practically in our cosmic backyard. It represents a unique opportunity to study a potentially habitable planet without having to travel across the galaxy, even if the logistics of communication and exploration remain daunting. Every observation, every photon of light collected from Proxima b is precious because it bridges this incredible gap, providing data from a world otherwise inaccessible. In essence, the 4.24 light-year distance forces us to rethink exploration and communication on a cosmic scale. Real-time interaction is impossible. Autonomous technology is essential, and patience becomes a scientific necessity. Yet, paradoxically, this same distance makes Proxima b the most tangible interstellar target humanity has ever discovered. Close enough for telescopes to detect atmospheric signals, close enough for theoretical probes to arrive within decades, and close enough to spark our imagination about what lies just beyond our solar system. It is a reminder of both the vastness of space and the ingenuity required to study planets beyond our own. While Proxima Centauri b has captured most of the attention, astronomers have reason to believe that the system may harbor additional planets, each with their own unique characteristics and potential for habitability. The discovery of multiple planets orbiting a single star is common in our galaxy. Nearly every well-studied star has at least one companion, and multi-planet systems are now understood to be the rule rather than the exception. In the case of Proxima Centauri, ongoing observations and analyses suggest that there may be more worlds orbiting this red dwarf, each contributing to the dynamism of our nearest stellar neighborhood. One of the most intriguing candidates is Proxima Centauri c, a tentative planet that may exist farther from the star than Proxima b. Detected through radial velocity measurements, which track the subtle gravitational wobbles of the star caused by orbiting planets, Proxima c is believed to be significantly larger than Earth, possibly a super-Earth or mini-Neptune, with a mass estimated at roughly 7 times that of Earth. Unlike Proxima b, which lies within the habitable zone, Proxima c orbits much farther out, around 1.5 astronomical units from the star, well beyond the region where liquid water could persist on the surface. This makes it a colder, more distant world, likely inhospitable by traditional Earth-like standards. Because Proxima c is farther from its parent star, it would receive only a fraction of the energy that Proxima b does, resulting in frigid surface conditions. Temperatures are likely extremely low, potentially leaving the planet enveloped in ice. However, this does not entirely rule out interest from scientists. Subsurface oceans or pockets of liquid water beneath thick ice layers heated by internal processes or tidal forces are theoretical possibilities. In addition, the planet's larger mass could allow it to maintain a thick atmosphere, potentially protecting any subsurface reservoirs from the harsh cosmic environment. Even in a frozen state, Proxima c represents a laboratory for understanding how planets form around red dwarfs and how their climates evolve over time. Observations of Proxima c also raise questions about the architecture of the system. The presence of multiple planets around Proxima Centauri would suggest that the system formed from a protoplanetary disk capable of producing diverse planetary types, both small, rocky worlds like Proxima b, and larger gaseous or icy bodies like Proxima c. Understanding the spacing, masses, and orbits of these planets can help astronomers reconstruct the system's formation history and predict whether additional planets might exist, potentially including smaller worlds closer in or intermediate planets in the habitable zone.
In addition to Proxima c, some studies have hinted at other smaller planetary candidates in the system. These potential worlds, while not yet confirmed, are suggested by subtle variations in Proxima Centauri's radial velocity that cannot be fully explained by the known planets alone. If confirmed, these planets could occupy different orbital regions, some potentially inside the habitable zone, some farther out in icy cold orbits. Each discovery would deepen our understanding of how planets interact gravitationally within a red dwarf system, and how stellar activity from a volatile star like Proxima Centauri influences planetary formation and long-term habitability.
The possibility of additional planets also emphasizes the need to consider orbital dynamics and stability. Proxima Centauri A is part of a triple-star system, along with Alpha Centauri A and B. While these stars are relatively distant from Proxima itself, their gravitational influence over millions of years could subtly affect the orbits of planets around Proxima Centauri, possibly shaping climate cycles or even affecting the likelihood of retaining atmospheres. Studying the orbital configuration of multiple planets in this system can provide insight into these complex gravitational interactions. Even if other planets in the system are too cold or too massive to support Earth-like life, they are scientifically valuable. Larger planets like Proxima C may provide clues about planetary formation around red dwarfs, the distribution of water and volatile compounds, and the potential for moons or ring systems. Moons orbiting such a planet could, in theory, possess their own microenvironments, perhaps even maintaining conditions suitable for life, much like Europa or Enceladus in our solar system. The Proxima system therefore represents not just a single habitable planet, but a diverse collection of worlds, each offering unique opportunities for exploration and discovery. Future observations using telescopes such as the James Webb Space Telescope, the Extremely Large Telescope, and next-generation radio velocity instruments could confirm the existence of Proxima C and other potential planets. They may also reveal details about their atmospheres, compositions, and surface conditions. If multiple planets exist in the system, astronomers would gain a complete picture of a nearby planetary system, something we currently only have for a few exoplanetary systems at much greater distances. In essence, Proxima Centauri b is just one piece of a larger, tantalizing puzzle. While it sits in the habitable zone and captures much of our attention for its potential to host life, Proxima C and other possible planets remind us that even our nearest stellar neighbor is a complex and dynamic system. Each planet, whether frozen, rocky, or gaseous, contributes to our understanding of planetary formation, evolution, and the diversity of worlds in the universe. The presence of multiple planets enhances the allure of the system, showing that the search for life and understanding of habitability extends beyond a single world and into the broader context of a nearby planetary neighborhood. The discovery of Proxima Centauri b carries profound implications for humanity, both scientifically and philosophically. For centuries, humans have looked up at the night sky and wondered whether other worlds like our own exist, whether life could thrive beyond Earth, and whether we might one day reach out to touch these distant planets. Proxima b brings these questions closer to home. At just 4.24 light-years away, it is not only the nearest potentially habitable planet we know of, but also a tangible reminder that our place in the cosmos is part of a much larger, more diverse universe. Proxima b challenges the historical notion that Earth might be unique. Its discovery reinforces a growing understanding among astronomers that Earth-like worlds may be common around stars in the galaxy, particularly around red dwarfs, which make up nearly 75% of all stars in the Milky Way. The fact that our nearest stellar neighbor hosts a rocky planet in the habitable zone suggests that potentially habitable worlds are not rare anomalies, but could exist in large numbers across the galaxy. This realization fundamentally reshapes our perspective on life in the universe, raising the possibility that the Milky Way might be teeming with planets capable of supporting life, even if intelligent life remains elusive. From a scientific standpoint, Proxima b serves as a natural laboratory for studying habitability beyond the solar system. Its proximity allows us to test theories about atmospheric retention, the impact of stellar flares, tidal locking, and climate dynamics under conditions very different from Earth. Each observation, from the potential detection of water vapor to the analysis of possible atmospheric composition, enhances our understanding of planetary science and guides the search for life elsewhere. In a sense, Proxima b represents a bridge between theoretical models and empirical observation, a world close enough for us to study directly rather than infer from distant light curves and indirect signals. Beyond science, Proxima b ignites the imagination and dreams of exploration. It forces us to confront the limits of our current technology while inspiring innovation. Concepts such as Breakthrough Starshot, advanced telescopes, and autonomous interstellar probes are motivated by the desire to reach, observe, and understand this nearby exoplanet. It becomes a concrete target for humanity's first steps toward the stars. a destination that transforms interstellar exploration from abstract theory into a potential future reality. The planet reminds us that even in a universe of staggering scale, there are worlds within reach, if we dare to develop the technology and vision required to get there. Philosophically, Proxima b challenges us to think about our cosmic perspective. For the first time, we can conceive of a world close enough that its existence might influence how we understand life, intelligence, and our role in the galaxy. Even if life does not exist on Proxima b, its presence tells us that planets with the conditions for habitability are not confined to our solar system. This insight fosters a sense of connection to the cosmos, a recognition that Earth is not the only cradle for life, and that the universe is a far richer, more varied place than previously imagined. The discovery also emphasizes human resilience and curiosity. Humanity has historically expanded its horizons from exploring continents to traversing oceans, and eventually reaching the Moon and Mars. Proxima b represents the next frontier, interstellar exploration. It challenges engineers, scientists, and dreamers to think in scales of light years, to develop technologies capable of surviving extreme distances, and to imagine civilizations capable of interacting with planets outside the solar system. The discovery turns philosophical curiosity into tangible objectives, catalyzing both technological advancement and cultural inspiration. Moreover, Proxima b serves as a symbol of hope and unity. The endeavor to study, observe, and eventually explore this planet transcends national boundaries. International collaboration is essential to design and launch the telescopes, instruments, and potential interstellar probes that will allow us to unlock its secrets. In this way, Proxima b represents not only a planetary neighbor, but also a shared goal for humanity, a target that unites us in the pursuit of knowledge, exploration, and the search for life beyond Earth. Even the possibility of finding life, even microbial, on Proxima b would be revolutionary. It would demonstrate that life is not unique to Earth, confirming that biology can emerge in varied environments and challenging long-held assumptions about the conditions necessary for life. Conversely, if the planet is inhospitable, despite being in the habitable zone, it would underscore the delicate balance required for life, refining our understanding of habitability and guiding future searches for planets where life is more likely to exist. In either outcome, Proxima b serves as a benchmark for exoplanetary science and the ongoing quest to understand the universe. Finally, Proxima b sparks a sense of existential reflection. It compels humanity to consider long-term survival, our capacity to reach beyond the solar system, and the broader implications of life existing elsewhere. For a species confined to one small planet, the knowledge that a potentially habitable world lies within a few light years invites us to contemplate interstellar futures, the possibility of colonization, exploration, or simply observing and learning from a nearby world. It reminds us that, despite our technological infancy on a cosmic scale, the universe is not inaccessible. There are reachable frontiers that challenge us to think big, innovate boldly, and dream expansively. In summary, Proxima Centauri b represents hope, knowledge, and ambition. It is a beacon that shows us that potentially habitable planets are near, that the tools to study them are within our reach, and that the drive to explore is intrinsic to humanity. It sparks imagination, fuels scientific inquiry, and inspires the next generation of explorers, engineers, and dreamers. In the vast, often overwhelming expanse of the cosmos, Proxima b is a lighthouse, guiding our curiosity, shaping our ambitions, and reminding us that the universe is both enormous and accessible, if we are willing to reach for it. As we bring our journey through the fascinating world of Proxima Centauri b to a close, it's worth pausing to reflect on what this planet represents for humanity. Just over 4 light-years away, Proxima b is, in cosmic terms, remarkably close, a neighbor in the vast expanse of the galaxy. Yet even this nearby world reminds us of the universe's immensity and complexity. The distances, the challenges of exploration, the harshness of its star, and the mysteries of its potential oceans and atmosphere all highlight just how extraordinary it is to discover a planet that might, in some ways, echo the conditions of Earth. Proxima b symbolizes human curiosity at its most ambitious. For decades, we have looked outward, scanning the heavens for signs of life, plotting the orbits of distant worlds, and dreaming of the day we might reach them. Each discovery, from the tiniest exoplanet to distant gas giants, has expanded our understanding of what is possible. Yet, Proxima b stands apart because it is tangible, a real physical place, close enough that, with future technology, we might one day observe it directly, analyze its atmosphere in detail, or even send robotic emissaries to its surface. It transforms the concept of interstellar exploration from abstract theory into something we can realistically imagine achieving. The planet also reminds us of the fragility and uniqueness of life on Earth. Observing a world in the habitable zone of a red dwarf star, potentially facing extremes of heat, cold, and radiation, makes us appreciate the delicate balance that sustains life at home. Earth's atmosphere, magnetic field, oceans, and climate work in perfect concert to create the conditions for life, and any disruption could have catastrophic consequences. Proxima b, whether it harbors life or not, serves as a cosmic mirror, reflecting both the challenges and opportunities for life beyond our solar system. Looking forward, Proxima b inspires dreams of exploration and innovation. From the precise measurements of telescopes like JWST and ELT to visionary projects like Breakthrough Starshot, humanity is taking the first steps towards bridging interstellar distances. Each observation, each experiment, and each theoretical model brings us closer to understanding not only Proxima b, but the broader universe of potentially habitable worlds orbiting countless stars. In this sense, Proxima b is not just a distant planet, it is a gateway to knowledge, a destination that challenges us to stretch the limits of our technology, our imagination, and our ambitions.
It also represents a collective aspiration for humanity. Exploration of distant worlds transcends borders, cultures, and generations. The questions raised by Proxima b about life, habitability, and the universe are questions for all of humanity. Our study of this planet exemplifies our shared curiosity and our shared drive to understand the cosmos, reminding us that, despite our differences, we are united by the desire to look up, learn, and reach outward. Ultimately, Proxima Centauri b is a symbol of both possibility and perspective. Even though it is only a few light years away, the challenges it presents underscore the vastness of space and the complexity of the universe. It reminds us that our journey to discover life beyond Earth has only just begun, that each new discovery is a stepping stone, and that the universe is far larger, far older, and far more intricate than we can yet comprehend. So, as we end this exploration, let Proxima b stand as a beacon of hope, curiosity, and ambition. It invites us to continue searching, questioning, and dreaming. It challenges us to advance our science, push our technology, and expand our understanding of life itself. Above all, it reminds us that while the universe is vast and filled with challenges, it is also filled with wonders, and humanity is only at the very beginning of its journey to uncover them. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.